Tonight, every photograph the James Webb Space Telescope has ever taken of deep space has the same problem. Tiny red dots, hundreds of them, scattered across the background of nearly every image, in places where nothing was supposed to exist. For 2 years, nobody could explain them. Now we know what they are. And the answer is not what anyone wanted to hear. We will see what is hiding inside each dot. A machine so violent it should not exist in a universe this young. The reason it changes everything we thought we knew about how galaxies are born, and the terrifying connection between those ancient monsters and the black hole sitting quietly at the center of our own Milky Way right now. If deep space keeps you watching, hit like and subscribe. Settle in. We begin. The image came back at 3 a.m. A team of astronomers had been waiting for months, watching their inboxes like surgeons waiting for test results. The James Webb Space Telescope had just finished its first real deep field observation, and the raw data was finally downloading to servers on the ground. Nobody slept that night. The team had reserved time on the telescope months in advance, fought for the allocation against competing proposals, and spent years building the software that would process the results. When the file appeared on the screen, the room went silent. Deep field means the telescope picks one tiny patch of black sky. A patch so small you could cover it with a grain of rice held at arm's length. Then it stares. Not for a second, not for a minute, for hours. Collecting every faint photon of light hiding in that darkness. Every signal too weak for a quick glance, stacking exposure after exposure until the faintest objects in the universe emerge from the noise. When Hubble did this back in 1995, it revealed thousands of galaxies nobody knew existed. Scientists expected Webb to do the same thing, just sharper, just deeper, just with better eyes. What came back was something else entirely. Scattered across the image, hiding behind galaxies, sitting between galaxies, sometimes right in front of them, were hundreds of tiny red dots. No shape, no structure, no spiral arms or glowing cores. Just small, bright, crimson points of light sitting in places where nothing was predicted. The team ran the data again. The dots were still there. They checked for instrument errors, light leaks, processing glitches, anything that could explain a false signal. The telescope was working perfectly. The dots were real. One of the researchers who saw the first images described the feeling as walking into a room you were certain was empty and finding footprints everywhere. Fresh ones, in every corner. Word spread fast. Within weeks, other teams pulled up their own Webb images from different parts of the sky. The same thing. Red dots. Everywhere, every single deep field shot was full of them. Not a handful, not a dozen. Hundreds per image. Over 1,000 were catalogued in the months that followed, and the number kept climbing. Astronomers started calling them little red dots. Not a technical name, just what they were. Small, red everywhere, the kind of name you give something when you have no idea what it actually is, and you need a label while you figure it out. Here is the first thing that made scientists nervous. These dots existed in the very first billion years after the Big Bang. The universe is about 13.8 billion years old. These objects formed when it was barely an infant, when the cosmos was still dark, still cooling, still assembling its first rough structures out of hydrogen and helium. Think of it this way. If the entire history of the universe were compressed into a single human lifetime of 80 years, the little red dots appeared in the first 6 years. Kindergarten, you were still learning how to hold a crayon. The universe was still learning how to build a star. And somehow, in that chaos, these blazing objects were already there. Objects this powerful, this bright, this compact, had no business showing up that early. The universe in its first billion years was supposed to be simple. Thin clouds of gas. The first clumsy stars flickering to life in the dark. Small, messy proto-galaxies slowly pulling together. Nothing like what these dots turned out to be. The The second thing that made scientists nervous was the brightness. You need to sit with this number for a moment, because it sounds made up. The most luminous of these dots were pumping out as much light as 250 billion suns combined, from a single point. Our entire Milky Way galaxy contains roughly 250 billion stars. It stretches 100,000 light-years across, a disk so wide that light itself takes 100,000 years to cross it. These dots were producing equivalent light from a space smaller than the distance between our Sun and its nearest neighbouring star. Smaller, in some cases, than our own solar system. Imagine taking every light bulb on Earth, every flashlight, every headlight, every stadium lamp, every LED screen, piling them all into your bedroom and turning them on at once. Now multiply that by a number so large your calculator gives up. That is the scale of energy these dots were producing from a space you could almost wrap your head around. Almost, something that's small producing that much energy was physically difficult to explain with any normal model. Stars alone could not do it. Known galaxies could not do it. Whatever was hiding inside those crimson points was doing something extreme. Something outside the catalogue. The first serious theory was star clusters. Dense, compact packs of young stars crammed so tightly together that their combined light blazed like a single point. The early universe was full of massive, hot, short-lived stars. Pack enough of them close together and maybe, just maybe, you get something this bright. The idea made sense on the surface. For about 3 months. Then someone ran the numbers, and the numbers killed the theory before it had time to settle in. To produce the observed brightness from stars alone, you would need billions of suns, all squeezed into a space roughly the size of the gap between our Sun and its nearest neighbour. The gravitational forces at that density would be catastrophic. Stars packed that tightly would crash into each other, merge and tear the whole structure apart in a few thousand years. Think of trying to park 1,000 cars in a single parking spot. You can force the first few in, but the pile crushes itself long before you reach the number you need. A star cluster that bright and that small cannot hold together. The physics of gravity tears it apart from the inside. You would be building a bomb and calling it a lighthouse. There was another problem. Stars produce a specific pattern of light. A fingerprint. When you spread starlight across its wavelengths, it shows a signature that astronomers can read the way you read a name tag. The light from the little red dots did not match any known stellar fingerprint. The pattern was wrong in ways that starlight alone could not produce. Something else was powering those dots. Something that burned hotter, stranger, and more violently than any star. The star cluster theory was dead by mid-2023, and whatever replaced it was going to have to explain something far more disturbing than brightness. But before we get to the answer, you need to understand why these dots stayed hidden for so long. Because the fact that we missed them for decades tells you something critical about how the universe keeps its secrets. Hubble stared at the same patches of sky for over 20 years. It photographed deep space more times than any telescope in history. It produced some of the most iconic images humans have ever made. If something was not in a Hubble image, the assumption was simple. It either did not exist, or it was too faint to matter. The little red dots were neither. They were in the same sky Hubble had been watching. They were bright enough to matter. Hubble just could not see them. The reason comes down to light itself. What your eyes see as visible light is only one thin slice of a much wider spectrum of energy. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all the same phenomenon, just vibrating at different speeds. Your eyes evolved to detect one narrow band. Everything outside that band is invisible to you, even though it is just as real. Hubble was built to see visible light and a sliver of ultraviolet. That sounds like plenty until you understand what happens to light after 13 billion years of travel through expanding space. Space is stretching. Every second, the fabric of the universe pulls apart in every direction. You cannot feel it. The stretch is too slow and too even to notice at human scales. But light feels it. When a photon travels through stretching space, the wave gets pulled longer. Longer waves shift toward the red end of the spectrum. Keep stretching long enough, billions of years long, and visible light becomes infrared. Below what your eyes can detect, below what Hubble was designed to capture. The little red dots were not hidden because they were dim. They were hidden because their light had been stretched completely out of Hubble's range. 13 billion years of cosmic expansion had redshifted everything they produced into infrared. The one frequency Hubble could not touch. Webb was built from the ground up to see infrared. Gold-coated mirrors designed to reflect infrared light with near-perfect efficiency. Special detectors cooled to temperatures colder than the void between galaxies. A sunshield the size of a tennis court was folded into the rocket and unfurled in space. Its job was to block the heat of the sun so the telescope's own warmth would not drown out the faint signals it was hunting. Every bolt, every wire, every surface on that machine was engineered around one goal: seeing light that every telescope before it had been blind to. The moment Webb opened its eyes and pointed at deep space, the dots appeared. Everywhere, in every direction, in every patch of sky it examined. They had been there all along. Hubble had been staring right through them for over 2 decades without knowing it. You could have pointed at any random square of sky and they would have been there, glowing in a colour your eyes cannot see, hiding in a frequency your best telescope could not reach. Here is why that discovery matters to you, beyond the headline. It means our entire picture of the first billion years of the universe was incomplete. Not slightly incomplete. Fundamentally incomplete. Every model astronomers built about the early cosmos was based on data that was missing an entire population of objects. Every simulation, every theory about how the first structures formed, all of it was built on an incomplete picture. The dots were not a rare anomaly. They were not a quirk of one unusual patch of sky. They were common enough to show up in the background of almost every image Webb captured. They were part of the furniture of the early universe, and humanity had no idea they existed until 2022. Every answer Webb gave about these objects immediately produced a harder question. If the dots were everywhere, what were they? Why did they appear only in that early period? What happened to them? Where did they go? Something made them disappear. And finding out what and why and what it means for everything you know about the cosmos took 4 more years. Something was hiding inside each dot, something that was not stars, not galaxies, not any structure that fit neatly into the catalogue of known objects. And the only candidate left was the one nobody wanted it to be. If stars could not explain the light, the source had to be something else. Something more powerful than any collection of stars could produce from that smaller space. Something that does not burn fuel the way stars do. Something that generates energy through gravity so extreme that matter gets torn apart at the edge of an abyss. A black hole. But not just any black hole. To produce 250 billion suns worth of light from a space smaller than our solar system, the black hole would have to be enormous. Millions of times the mass of our sun, actively feeding, swallowing gas and dust at a rate that would make it one of the most violent objects in the early universe. That answer solved one problem and immediately created 2 more. Because black holes that size should not exist in the first billion years, and black holes that are actively feeding should be easy to find. They should be screaming so loudly that you could spot them from across the observable universe. To understand why the silence was so alarming, you need to know what a normal feeding black hole actually looks like to our instruments. Quasars are the benchmark. A quasar is a supermassive black hole actively devouring enormous amounts of gas. It is the brightest sustained object in the known universe. If you could somehow see one with your naked eye from across the cosmos, it would outshine the galaxy it lives in by a factor of 1,000. Quasars fire jets of superheated plasma thousands of light years into space at nearly the speed of light. They flood their surroundings with X-rays, radio waves, and ultraviolet radiation so intense that astronomers can detect them from the far edge of what our telescopes can reach. When astronomers first discovered quasars in the 1960s, the signal was so loud they thought they were looking at nearby stars. The light was that bright, that overwhelming. It took years of careful work to realize those objects were sitting billions of light years away and were among the most distant things ever observed. Now here is what should bother you. The little red dots should be quasars. Based on the energy output alone, based on the mass of the black holes estimated inside them, they should be lighting up every instrument on Earth. Any telescope designed to detect an active black hole should have caught them immediately. Every detector came back empty. No X-rays, no radio waves, no ultraviolet bursts. Just the soft red glow of heated gas. Quiet, hidden, as if the most violent objects in the young universe had learned how to hide. The answer came slowly, built from years of careful observation. The black holes inside the little red dots are buried. Not buried in dirt, buried in gas. Incredibly thick, incredibly dense clouds of ionized gas that surround the black hole like a cocoon. Think of the loudest concert you have ever imagined. Drums shaking the walls, bass rattling your ribs, noise so intense you feel it in your chest. Now seal that concert inside a room with walls 100 feet thick, packed solid with material that absorbs every frequency of sound. From outside the walls, you hear almost nothing. A faint hum. Maybe a vibration in the floor. That is what the little red dots are. Except instead of sound, the walls are absorbing radiation, and the concert inside is a supermassive black hole consuming matter at a ferocious rate. The cocoon is not a thin shell, it is a churning, turbulent barrier of gas so dense that X-rays, radio waves, and ultraviolet light cannot punch through. The radiation gets absorbed, the energy gets trapped, the outer layer of gas glows red from the absorbed heat, and that faint red glow is all we see from the outside. Inside the cocoon, the violence is almost beyond description. Gas orbits the central black hole at speeds of roughly 670,000 miles per hour. To put that in perspective, a commercial aeroplane flies at about 550 miles per hour. A bullet leaves a gun at about 7,400. The gas inside these cocoons is moving almost 400 times faster than a bullet. At that speed, you could travel from Earth to the Moon in about 1.3 seconds. The gas does not drift. It tears. It smashes into itself constantly. Every collision generates heat so intense that atoms are stripped of their electrons, creating a permanently charged, permanently reactive storm of plasma spinning around a point of infinite gravity. The temperatures inside these cocoons reach millions of degrees. Hotter than the surface of any star. Hotter than the core of most stars. A furnace powered by gravity itself. The whole system sustains itself through its own fury. The radiation from the black hole ionizes the gas. The ionized gas stays dense. The dense gas traps more radiation, and the black hole keeps feeding, hidden behind a self-sealing curtain of fire that grows thicker the harder the monster inside pushes against it. You have never seen anything like this in your life. You have never been near anything like this. The closest comparison your brain can reach for is a hurricane, but a hurricane is a gentle breeze compared to the chaos inside one of these cocoons. The storm inside a little red dot would vaporize everything you know, everything you have ever touched, in a fraction of a second. And it has been raging since before the Earth existed. Something was buried alive in the early universe. And it was growing. The disguise was so complete that these objects fooled every detection method available for decades. Hubble missed them. Radio telescopes heard nothing. X-ray satellites returned blank fields. And there were over 1,000 of them, sitting in the background of every deep field image, hiding in plain sight. Right in front of us, The whole time. If you had told an astronomer in 2020 that the early universe contained a whole category of powerful objects nobody had discovered yet, they would have laughed. Everything was supposed to be accounted for. The census of the early cosmos was supposed to be close to complete. It was not even close. Then, in July 2024, one of the dots broke even the already broken rules. They nicknamed it the Cliff. Among the little red dots, which were already the most compact, most luminous, most baffling objects from the first billion years, the Cliff stood apart. Its light output was higher, its size was smaller, the gas orbiting inside it was faster than anything the models could comfortably explain. The gas inside the Cliff moved at speeds approaching 670,000 miles per hour in tight, chaotic orbits around whatever sat at the centre. The gravitational field required to hold gas at that velocity pointed to a central mass at the extreme upper end of the range. Millions upon millions of solar masses crammed into a space that would fit inside the gap between our Sun and its nearest star. Some researchers called the Cliff a rare outlier, a freak product of perfect conditions, a massive initial seed sitting at the junction of multiple cosmic gas streams, fed continuously without the interruptions that normally slow a black hole's growth. Others saw something darker. If the best physics available, even stretched to its absolute limit, still could not fully explain a single object, then maybe the physics itself was missing something. Maybe the rules you learned in school, the ones that govern how objects grow and how gravity works at the extremes, were not the complete set. The Cliff sits in the data like a crack in a wall you just moved into, small enough to ignore if you want to, too clean to explain away if you are honest with yourself. And the longer you look at it, the more you wonder what else is behind the surface. The monsters were buried alive, fed in darkness, growing in silence. And nobody could explain how they got so big, so fast, in a universe that young. Not the theorists, not the observers, not the engineers who built the telescope that found them. That is the question that keeps everyone awake. And the answer is terrifying, not because it involves something new. It is terrifying because it means something old, something fundamental, something you thought was settled, is broken. But the story of the dots took one more turn before the timeline question even landed. Because when astronomers looked at the red dot population through ultraviolet light, the category split in half. For the first year, everyone treated the little red dots as one thing. One type of object. One explanation. Buried black holes in cocoons. Simple, clean, unified. Then, someone ran an ultraviolet test. Ultraviolet light sits just above visible light on the spectrum. Shorter wavelengths. Higher energy. It interacts differently with matter than infrared does, and it can reveal features that infrared hides. When astronomers pointed ultraviolet sensitive instruments at the dots, about 70% of them looked exactly as expected. Compact, circular, consistent with a point-like energy source surrounded by a glowing shell. The buried black hole model. Clean and confirmed. The other 30% transformed into something nobody recognized. In ultraviolet light, these objects lost their sharp circular shape entirely. They became fuzzy, extended asymmetric blobs with irregular edges, multiple brightness peaks, and light distributed in patterns that had no obvious center. Some looked like smears, others looked like patches of spilled paint with no structure at all. This was not what a buried black hole should look like at any wavelength. Something else was going on inside that 30%. Something that did not fit the single explanation model. Maybe those dots were not buried black holes at all. Maybe they were something else entirely, dense star-forming regions producing light through a completely different mechanism. Or maybe they were black holes in a different phase. Caught at a moment when the cocoon was not yet fully formed, or already starting to crack apart. The split is still being debated. Papers are being published monthly, each one offering a slightly different interpretation. Some argue the 30% are simply younger versions of the same object, still assembling their cocoon. Others argue they are a completely separate population that happens to look similar in infrared but is fundamentally different in nature. What the Webb split tells you, even before it is resolved, is that the early universe was more complicated than anyone assumed. The category little red dot may not be a single category at all. It may be a filing cabinet stuffed with different objects that only look the same when you view them in one narrow band of light. Open the drawer and the contents scatter. That complexity is not a problem. It is a clue. Every time astronomers find more variety inside a population, it means the underlying physics has more moving parts than the models assumed, and more moving parts means more to discover. There is a deeper question hiding behind all of this, one that most astronomers do not talk about in public, but that you can hear in the careful language of their papers. If the timeline is broken, if the growth rate exceeds what known physics allows, then maybe the problem is not with the black holes. Maybe the problem is with our understanding of gravity itself. General relativity describes gravity as the bending of space and time around massive objects. It works perfectly in every environment we have tested it. Solar systems, binary stars, neutron star collisions, black hole mergers. The equations hold, the predictions match, but the conditions inside a little red dot are more extreme than anything we have tested directly. A supermassive black hole feeding at or above the Eddington limit, surrounded by a turbulent cocoon of superheated plasma growing at a rate the models say is impossible. What if gravity behaves slightly differently under those conditions? What if there is a regime we have not reached yet where the rules bend? Nobody is ready to say that. Not yet. The data is too new, the error bars are too wide, the simpler explanations have not been fully exhausted. But the possibility is there, floating in the background of every conference talk about the red dots. A quiet thought that nobody wants to be the first to publish. If the little red dots force a revision to our understanding of gravity at extreme scales, the implications would reach far beyond astrophysics. It would touch cosmology, particle physics, quantum gravity, the nature of space-time itself. It would be one of the biggest shifts in fundamental physics since Einstein published general relativity in 1915. That is probably not what is happening. Probably the answer is simpler. Bigger seeds. Faster feeding. Mass overestimates. The boring explanations tend to win in science, but the dots have pushed the boring explanations to their limits, and the limits are creaking. Here is what the little red dots have already changed, regardless of how the remaining questions are answered. They have changed the timeline. The first structures in the universe were not simple, gradual, orderly assemblies of gas and stars. They were violent. They were hidden. They were powered by monsters that grew faster than anyone thought possible. They have changed the origin story. Galaxies did not grow black holes. Black holes grew galaxies. The seed came first. The structure came second. The foundation was laid before the house was designed. They have changed the search. Astronomers are no longer just mapping what the universe looks like. They are hunting for the buried ancestors that built it. Looking for the missing generation. Tracing the bloodline from a tiny red dot 13 billion years ago to the quiet black hole sitting at the center of the galaxy you are standing in right now. And they have changed you. Not physically. You are made of the same atoms you were made of before the dots were discovered. But you know something now that you did not know before. You know that the universe you live in was organized by buried monsters. That the quiet, peaceful night sky above your head is the aftermath of the most violent era in cosmic history. That the place you call home was built on a foundation of fire and silence and gravity so extreme that it bends the rules of physics. You are not separate from that story. You are the latest chapter of it. To understand why the answer is terrifying, you need to understand how black holes are supposed to grow. Because the monsters buried inside the little red dots did not follow the rules. They skipped steps. They cut in line. And the universe has no explanation for how they pulled it off. Start with what you know. A black hole forms when a massive star runs out of fuel and collapses under its own weight. The core crushes inward so fast and so hard that nothing can stop it. Not the pressure of atoms pushing back, not the force of electrons resisting compression. Nothing. The core falls through every floor in the building and keeps falling. What is left behind is a point of gravity so intense that light itself cannot climb out. That is a stellar black hole. It weighs somewhere between 5 and 50 times the mass of our Sun. Heavy by any standard you can imagine, but compared to the monsters inside the little red dots. A stellar black hole is a pebble next to a mountain. The black holes hiding in those crimson dots weigh millions of times the mass of the Sun. Some estimates push past 10 million. To grow from a pebble to a mountain, a black hole needs time. A lot of time. Here is how growth normally works. A black hole sits in space surrounded by gas. Gravity pulls the gas inward, but the gas does not fall straight in like a rock dropped down a well. It spirals. It forms a flat, spinning disk around the black hole, getting faster and hotter as it tightens. The friction in that disk heats the gas to millions of degrees. At that temperature, the gas radiates energy outward. Light, heat, X-rays. A torrent of radiation pushing back against the incoming flow. Think of trying to drink from a fire hose. The harder you suck, the harder the water blasts back into your face. At a certain point, you cannot drink any faster, because the back pressure matches your suction. A black hole faces the same problem. The faster it eats, the more radiation it spits out, and that radiation pushes against the incoming gas like a wind blowing against a river. At a certain feeding rate, the outward radiation exactly balances the inward pull of gravity. The gas stalls. The feeding caps out. The black hole cannot grow faster no matter how much gas is available around it. This limit applies everywhere in the universe. To every black hole. In every galaxy. At every point in cosmic history. It is one of the most fundamental constraints in astrophysics, and the little red dots appear to have violated it. Physicists call this the Eddington limit. It is named after Arthur Eddington, the same astronomer who confirmed Einstein's theory by watching starlight bend during a solar eclipse. The Eddington limit is the maximum rate at which a black hole can swallow matter under normal conditions. Think of it as a speed limit posted on the highway. You can floor the gas pedal all you want, but the road itself will not let you go faster. At the Eddington limit, a black hole can roughly double its mass every few 100 million years. That is the fastest the universe allows under standard rules. No shortcuts. No exceptions. That sounds fast enough until you do the math for the little red dots. And the math is where everything falls apart. Start with a stellar black hole. Say 50 solar masses. That is what you get when a massive star collapses at the end of its life. 50 suns crammed into a point. Now double it. 100. Double again. 200. 400. 800. Keep doubling. You need to reach 10 million solar masses to match what is hiding inside the brightest red dots. That takes roughly 18 doublings. At the Eddington limit, under absolutely perfect conditions, with no interruptions, no pauses, no disruptions of any kind, 18 doublings takes about 2 billion years. The universe was less than 1 billion years old when these dots appeared. Less than 1 billion. You are trying to cram 2 billion years of growth into a window half that size. It is like being told a skyscraper was finished 6 months after the concrete was poured, when the blueprints alone take a year. The timeline does not work. You can twist the numbers every way you want. You can assume perfect feeding, zero downtime, maximum efficiency. The math still comes up short. This is the part that shook the field. Not the dots, not the silence, not the cocoons. The timeline. The raw, stubborn impossibility of growing something that massive but quickly using every known mechanism in physics. Something broke. Either the rules of growth are wrong, or the starting conditions were different from what we assumed, or both. 3 explanations have been proposed. Each one solves part of the problem. None of them solve all of it. The first says the seeds were bigger. Maybe these black holes did not start from collapsing stars at all. Maybe, in the dense, chaotic conditions of the very early universe, entire clouds of gas collapsed directly into black holes without forming stars first. No star phase. No gradual build-up. Just a massive cloud of primordial hydrogen. Hundreds of thousands of solar masses. Falling inwards so fast that it skips every step and becomes a black hole in one violent event. This is called direct collapse. And it changes the math dramatically. If your seed is not 50 solar masses but 100,000, you need far fewer doublings to reach the millions. The head start is enormous, like starting a race 10 miles ahead of the other runners. You still have to run, but you have to run a lot less. The problem with direct collapse is that it requires very specific conditions. The gas cloud has to be massive. It has to be free of heavy elements like carbon and oxygen. Those elements help gas cool down and break into smaller clumps that become stars instead of collapsing as one mass. And the cloud needs to be bathed in a particular kind of ultraviolet radiation that keeps it from breaking apart prematurely. Those conditions are narrow, like threading a needle while wearing boxing gloves. Whether the early universe produced them often enough to explain over 1,000 little red dots is an open question that nobody has answered yet. No one has confirmed a single direct collapse event through observation. The theory works on paper. The universe has not signed the receipt. The second explanation says the feeding rate was faster than the rules allow. Maybe in the early universe, when matter was packed tighter and the distances between structures were shorter, some black holes managed to exceed the Eddington limit. Not constantly. In bursts. Picture a city in the middle of a flood. Water is not just falling from the sky. It is rushing in from every direction along every road, every valley, every drainage channel. The city centre receives more water in a single hour than it would normally see in a month. That is what the early black holes may have experienced. In the first billion years, the universe was far more compact than it is today. Matter had not yet spread out into the vast, thin web of filaments and empty voids that you see in the modern cosmos. Instead, gas was concentrated in dense streams and knots, flowing along gravitational channels that connected early structures to each other. Astronomers call these cosmic filaments. Think of them as rivers. Rivers of primordial hydrogen and helium flowing directly toward the gravitational wells where the first black holes sat waiting. When a dense filament connects to a black hole, the inflow rate can temporarily swamp the radiation pushing back. The gas floods in faster than the light can push out. For a brief window, the black hole eats faster than the Eddington limit says it should. It drowns in fuel. Then the burst passes. The radiation catches up. The feeding drops back to normal. Then another filament connects, another burst. Another surge of growth. This model fits some of what we see. The gas inside the red dots appears turbulent and chaotic, fed from multiple directions at once. Not the clean, orderly disk you find around modern quasars. The mess matches the flood theory. But sustaining Super Eddington bursts over hundreds of millions of years requires nearly perfect conditions. One long gap without a filament connecting, one sustained period of low feeding, and the black hole falls behind schedule permanently. The margin for error is 0. The third explanation is the one nobody likes to say out loud. Maybe the masses are wrong. The methods used to weigh these ancient black holes are indirect. You cannot put a black hole on a scale. You cannot fly a probe past one and measure the pull. What you do is measure the speed of gas orbiting around it. The faster the gas moves, the stronger the gravitational field holding it in orbit. From the speed, you calculate the mass. But that calculation depends on assumptions. What shape is the gas in? A thin, flat disk? A thick, puffy cloud? A chaotic mess with no clear structure? Are you looking at it from above, from the side, or at an angle? Each answer changes the number you get. And for objects 13 billion light-years away, shrouded in thick cocoons of ionized gas, the answers to those questions are not clean. If the true masses are lower than current estimates suggest, the growth timeline becomes less impossible. A black hole that weighs 2 million solar masses instead of 10 million needs far fewer doublings. The math gets easier, the panic gets smaller. But here is the problem with that comfort. The mass estimates have been checked. Multiple teams, multiple methods, different instruments, different assumptions. And they keep landing in the same uncomfortable range. Not identical numbers, but the same ballpark. Millions of solar masses. In less than 1 billion years. You can squint at the error bars and hope the true answer is at the low end. Some physicists do exactly that, but the error bars are not large enough to make the problem disappear entirely. They just make it slightly less impossible. And slightly less impossible is still impossible. The honest answer, the one that appears in the conclusions of the actual papers, is that nobody knows which explanation is correct. It could be direct collapse. It could be super Eddington feeding. It could be a mass overestimate. Most likely it is some combination of all three. A bigger seed than expected, fed faster than normal, with a true mass slightly lower than the headline number. Stack those three adjustments together, and you might close the gap. Might, but might is not a solution. It is a prayer dressed up in statistics, and the gap between what the math allows and what Webb is showing is still the largest unresolved question in modern astrophysics. The textbook model of black hole growth, the one taught in every physics classroom on the planet, cannot explain what Webb is seeing without being rewritten. The rules need new pages, and nobody has agreed on what those pages should say. If you are still here, you belong here. Subscribe if you want to keep going deeper. But the timeline problem is only half the story, because the little red dots do not exist in the modern universe. You will not find them in any telescope image of nearby galaxies. They appeared only in the first billion years. Then, they vanished. Every single one. Gone. Understanding where they went is where the story turns personal. But first, you need to understand what it means that there were so many of them. Over 1,500 have been catalogued so far, and that number is based on the tiny fraction of the sky that Webb has examined in deep field mode. The telescope has looked at patches of sky so small that you could cover each one with a fingertip. If you scaled the count up to the full sky, the total number of little red dots in the first billion years could be in the millions. Millions of buried supermassive black holes in a universe barely old enough to have stars. That changes the picture of the early universe completely. It was not a quiet nursery where the first gentle structures slowly took shape. It was a minefield, a dark sea filled with hidden engines of gravity and fire, each one growing in silence, each one shaping the space around it, each one destined to become the core of a galaxy that would last for billions of years. The early universe was not peaceful. It was the most violent era in cosmic history, and we did not even know it until a telescope built to see invisible light pointed at the dark between the stars and found footprints everywhere. The cocoon cannot last forever. Remember the balance. Radiation pushing outward from the feeding black hole at the centre. Dense gas pushing inward under the force of gravity. The system holds as long as both sides stay matched, but the balance is fragile. Temporary, one side always wins eventually. As the black hole grows heavier, it feeds harder. More gas falls in, more radiation pours out. The cocoon absorbs the energy and heats up. The temperature climbs. The pressure inside the shell builds and builds and builds. Think of a pressure cooker with a faulty seal. The heat rises. The steam builds. The lid strains. It holds. It holds. It holds. Then it does not. The release is sudden, violent, and irreversible. When the cocoon of a little red dot finally cracks, the transformation is dramatic. The buried black hole is exposed to the open universe for the first time. Every form of radiation that had been trapped, absorbed, sealed inside for millions of years erupts outward. X-rays blast into the void. Radio waves fire across millions of light years. Jets of superheated plasma, compressed and stored behind the cocoon walls for eons, punch through into open space at nearly the speed of light. The silent monster becomes a screaming one. And we have a name for what it becomes. It becomes a quasar. The brightest, loudest, most violent sustained object in the known universe, the same kind of object astronomers have been studying since the 1960s. The same kind that can outshine an entire galaxy by a factor of 1,000. The same kind that fires jets visible from across the observable universe. The little red dots were quasars before the shell broke, quasars still sealed inside their birth cocoon, feeding in the dark, growing in silence, waiting for the moment when the pressure inside exceeded the strength of the walls. When a quasar finally fires up, it is one of the most spectacular events in nature. For a few 100 million years, the object that had been hiding in total silence becomes one of the brightest sustained sources of energy in the entire universe. You could see it from billions of light years away. Entire galaxies are outshone by a single point at their center. But the blaze cannot last forever. As the universe expands, the cosmic filaments that fed the monster stretch and thin. The rivers of gas slow to a trickle. The accretion disk cools, the jets fade, the quasar dims. Over hundreds of millions of years, the brightest object in the cosmos goes quiet. But the black hole itself does not disappear. It does not evaporate. It does not shrink. A black hole, once formed, is permanent on any timescale that matters to the universe. It just stops eating. It sits there. Massive, dark, patient at the center of a growing swarm of stars, gas clouds and dust that has been gathering around it since the moment it was born. That swarm becomes a galaxy. And the black hole becomes its heart. This is where the story stops being about the ancient universe and starts being about you. Every large galaxy in the observable universe has a supermassive black hole at its center. Not some galaxies, not most galaxies. Every single large galaxy that astronomers have examined closely enough has one. It is as universal as having a heartbeat. Wherever you find a major galaxy, you find a monster at its core. Our own Milky Way is no exception. Its black hole sits 26,000 light-years from where you are right now. In the direction of the constellation Sagittarius, hidden behind thick clouds of gas and dust that block your view in visible light. Its name is Sagittarius A star. It weighs about 4 million times the mass of our Sun. Right now, Sagittarius A star is quiet. It is barely feeding. The gas around it has thinned to almost nothing. The jets are gone. The accretion disk is a faint whisper compared to what it once was. If you could look at it directly, you would see almost nothing. A dark spot surrounded by a faint glow. The engine is idling. But it was not always quiet. 4 million solar masses did not appear from nothing. That mass was built up over billions of years of feeding, merging and growing. And the question that the little red dots raise is not just where that mass came from. It is whether Sagittarius A star played a more active role in creating the galaxy around it than anyone previously understood. Think about what it means for you specifically. If the black hole was the seed, and the galaxy formed around it, then the structure you live inside was shaped from the very beginning by a buried monster. The spiral arms of the Milky Way, the position of the sun within them, the cloud of gas that condensed into our solar system, all of it was influenced by the gravitational field of the black hole at the center. The sun sits about 2/3 of the way out from the core, in a quiet arm called the Orion Spur. That position is not random. It was shaped by the dynamics of how the galaxy formed. and how the galaxy formed was shaped by the mass of the central black hole. A black hole that may have once been a little red dot feeding in silence behind a wall of fire. Your address in the cosmos was written by a monster. There is something else worth sitting with. Here is something else worth sitting with. The early universe was full of buried monsters. Those monsters seeded galaxies. Those galaxies produced stars, then planets, then life. Your existence is downstream from the most violent objects in the cosmos. The chain is direct. Black hole to galaxy, galaxy to stars, stars to heavy elements to planets, planets to chemistry, chemistry to you. Every step in that chain leads back to a buried dot in the first billion years. Every step depends on the monster at the center organizing the matter around it into the structures that eventually gave rise to everything you know. That is not a metaphor. That is the causal chain. And the little red dots sit at the beginning of it. Now connect the dots. The little red dots were buried supermassive black holes in the first billion years. They grew fast, hidden in cocoons of fire. The cocoons broke. The quasars blazed. The quasars faded. The black holes survived. Galaxies formed around them. The supermassive black holes sitting at the centers of galaxies today, including ours, may be the direct descendants of the little red dots. Take a moment with that. The thing at the center of your galaxy, the quiet, dark, patient anchor that holds 100 billion stars in orbit around it, was once a tiny red dot. Buried alive, feeding in silence, growing in the dark. Before the sun existed, before the Earth existed, before the Milky Way itself had finished forming. You live inside the aftermath of one of those monsters. The galaxy you call home was organized around it. The stars that forged the iron in your blood orbit it. The solar system you ride through space in moves at over 500,000 miles per hour around the center of the galaxy because of it. The ground under your feet exists because of it. The air in your lungs, the screen in front of your eyes, all of it sits inside a structure seeded by a buried monster born 13 billion years ago. The thing buried at the center of your galaxy was once buried alive in a cocoon of fire. And you are living inside its legacy. This is why the discovery of the little red dots is not just another astronomy headline you scroll past and forget. It is a rewrite of the origin story, not just for our galaxy, for every galaxy in the observable universe. For decades, the standard model of galaxy formation told a clean story. Black holes and galaxies grew together, side by side. Gradually, the process worked like this. A cloud of gas in the early universe begins to collapse under gravity. Stars form inside it. The brightest stars die quickly and scatter heavy elements. More stars form. The structure grows. Gas trickles toward the center and feeds a small black hole that sits there like a drain in a bathtub. The black hole grows slowly in proportion to the galaxy around it. A partnership. A mutual construction project unfolding over billions of years, like two vines climbing the same wall. That model was elegant. It matched the data from nearby galaxies. It fit the computer simulations. It explained the tight correlation between galaxy size and black hole mass. It was the kind of clean, logical story that scientists love, because it makes the universe feel orderly. Comprehensible, fair. The little red dots broke that story in half. The black holes came first. They formed in the first billion years. They grew to enormous size behind their cocoons, while the galaxies around them had barely begun to take shape. The black hole was not a passenger growing alongside the galaxy. It was the seed, the anchor, the gravitational center that pulled everything else into orbit around it. Think of it like finding out that the foundation of your house was not poured after the plans were drawn. The foundation was already there, laid before the architects arrived, before the neighborhood existed, before the roads were built, and the house, the whole neighborhood, was constructed on top of it because there was nowhere else solid enough to build on. That flips the model. The universe's architecture is not a democracy where black holes and galaxies grow together. It is a monarchy. The black hole sits at the center, and everything else falls into place around it. If black holes seeded galaxies instead of growing alongside them, the relationship between black holes and their host galaxies needs to be rethought from scratch. For decades, astronomers noticed a tight link between a galaxy's size and the mass of its central black hole. That link stops being a coincidence and starts being a consequence. The galaxy did not grow the black hole. The black hole organized the galaxy. The implications ripple outward into every corner of astrophysics. How stars form in the first place, how galaxies collide and merge, how the large-scale structure of the cosmos, the vast web of filaments and voids stretching across billions of light years, assembled itself from the chaos of the first billion years. All of it connects back to those buried dots. All of it may need to be recalculated with the black hole as the starting point instead of a side effect. And we almost missed them entirely. If Webb had been built to see a slightly different wavelength, we might never have found them. If the telescope had launched a decade later, we would still be telling the old story. The entire foundation of the modern universe was hiding in plain sight, painted in a colour our eyes cannot see. What comes next is a hunt. And it is already underway. DREST is still observing. Every week, new images arrive from the telescope. More little red dots are being catalogued every month. The population count has already passed 5,500, and with every new deep field image, the number climbs. The more dots they find, the stronger the statistical power to test the competing theories. How common were direct collapse seeds? Were they the exception or the rule? How often did super Eddington feeding actually happen? Was it a rare burst or a sustained phase? Is there a transitional population, a missing generation of objects caught halfway between the red dot phase and the quasar phase that nobody has identified yet? Some teams are hunting for exactly that missing generation. They are looking for dots caught in the act of breaking open. Half-buried monsters with one jet punching through a cracking shell while the other side is still sealed. The cocoon mid-collapse, the monster mid-reveal. Finding one would be like photographing a butterfly with one wing still inside the chrysalis. A single frozen moment of transformation. It would confirm the connection between the dots and the quasars in a way that no indirect argument could match. It would be one of the most important observations in the history of astronomy. And several groups believe they are close to finding one. Other teams are approaching from a different angle entirely. They are studying the supermassive black holes in nearby galaxies close enough to examine in detail, and trying to trace their ancestry backward. If those black holes descended from little red dots, there should be fingerprints in the galaxies surrounding them. Chemical fingerprints. Signatures left behind by the violent hidden feeding era. Patterns in how the galaxy's oldest stars are arranged that only make sense if the black hole was already massive before the galaxy itself was fully assembled. Some of those fingerprints may already exist in data that was collected for entirely different reasons. Old surveys, archived images, spectroscopic measurements taken a decade ago and filed away. The answer might be sitting in a database right now, labelled as something else, waiting for someone to ask the right question. The data is coming in slowly. The questions are enormous. The answers will take years, maybe decades. But the direction of the search has already shifted in a way that cannot be undone. Before 2022, the story of the early universe was simple. Gas, gravity, stars, galaxies, everything assembling gradually in the dark, piece by piece, over billions of years. A slow, patient construction project with no shortcuts. Now the story has monsters in it. Buried ones. Hidden ones. Monsters that grew faster than physics said they could. That hid behind walls of fire nobody could see through. That became the foundations on which every galaxy in the observable universe was built, including yours. The iron in your blood was forged inside a star. That star was born inside a galaxy. That galaxy was built around a black hole. And that black hole, the seed of everything you know, was once a tiny red dot, buried alive in a cocoon of fire, growing in silence, in the dark, before the Earth existed, before the sun existed, before anything you could recognize as home had even begun to form. You are the downstream consequence of a monster that nobody knew about until 2 years ago. And the telescope that found it is still watching, still counting, still scanning the oldest light in the sky, finding more of them in every image it takes. Somewhere out there, right now as you listen to this, due east is pointed at a patch of sky no wider than a grain of sand. Its mirrors are collecting photons that have been travelling toward you for 13 billion years. Some of those photons will land on the detector and reveal another red dot, another buried monster, another ancestor, and one of them might be the seed that eventually became the black hole at the centre of your own galaxy. Tiny red dots, hundreds of them, scattered across the background of every deep field image ever taken, footprints in a room everyone thought was empty. The loudest silence in the early universe, a timeline that breaks the rules, ancestors buried alive in cocoons of fire, a galaxy formation model turned upside down. And you, here, tonight, made of atoms that were forged in stars that orbit a direct descendant of one of those ancient, hidden, impossible monsters. That is enough for tonight. Good night. If you felt this one, drop buried alive in the comments. We want to know who else is out here. What do you think came first, the black hole or the galaxy? Does it change the way you think about the Milky Way, knowing there is a descendant of one of these monsters sitting at the centre of it right now? Tell us in the comments. Share this with someone who looks at the night sky and wonders what is really hiding in the dark. Someone who stays up late asking questions that most people never think to ask. They belong here. Subscribe if you want to keep going deeper. Hit the bell. We have barely scratched the surface of what Webb is finding, and the next discovery might be even harder to believe. We are the ones who stay up late asking questions the universe has not answered yet. And we are just getting started.